So good morning and welcome back. So we were looking into biasing a transistor using constant current source, and one of the ways of biasing that we explored was this. And the reason that this works is because if the threshold voltage of the transistor changes or the mobility of the transistor changes, then the VGS adjusts accordingly. So the trick is to ensure that whenever you are trying to feed in a current, you have to find out a way of ensuring the VGS gets adjusted automatically. Because ultimately, as far as the transistor is concerned, VGS is the cause and current is the effect. Just because you want to fix the current by using a current source doesn't oblige the transistor to adjust the VGS automatically. You'll have to do it in some way. So in this case, we saw this is one of the ways of achieving the same. So again, if the threshold voltage, for example, increases because the temperature increase, what's going to happen? What's going to happen to the VGS? Let's say the threshold voltage increase after you biased it like this. It will increase, right? So one of the three things, right? It will either increase, decrease, or no change. So it's going to increase because in order to keep the current same, the overdrive has to remain same, right? In order to keep the current same, the overdrive has to remain same. If threshold voltage increases and overdrive remains the same, which means VGS has to increase, right? So now the thing that, again, this is, I am harping on the same thing again and again. This logic is not applicable if you connect your current source like this. Just keep it floating, right? Even though one might argue that this current is still flowing through the transistor, yes, it can, the way we have sketched it, but it doesn't ensure that the transistor will remain in saturation. Okay, so, and also one might say that, what if I connect like this? Yes, this will work only under certain conditions where the VGS is exactly that of that value that is required to sink in the current of I0. Moment the threshold voltage changes, then it will, that equality will not hold and the transistor will go out of saturation. So this is an example of a bad biasing. Okay, so if you find something like this, you know that something is wrong. Okay, fine. So now we can extend these ideas of, extend the arguments of biasing with constant current source by observing the following. So in a transistor, ultimately, we can feed in the current source at two places. Either we can feed in the current source into the drain, or we can take the current source out from the source, right? So one example that you already did, one analysis you have already done in previous lectures, in the last quiz and the previous assignment also, was the current source was connected here, right? So the reason, so in the today's lecture, we'll try to see why that works or what are the problems associated with it. So in general, you can always, in general, in a transistor, the control terminals are gate and source, right? And the observing terminals are drain and source. That's typically those are the typical places where you apply the inputs and you take the output. So one might argue that if that is the case, then there are essentially four possible combinations of feeding the input and taking the output, right? I can apply the input at the gate or at the source, and I can observe the output either at the drain or at the source. So four possible combinations. So if that is the case, I can argue that, so this particular configuration that we talked about was doing the following. So in this case, I0 was applied. So this is apply I0 at drain, observe drain voltage and correct gate voltage, right? This was what we were doing, right? We applied the current source at the drain, then we observed the drain voltage is going up and down. Based on that observation, we took a decision. What should we do to the gate, right? So the corrective action was, so this was the observation and this was the correction, right? The connection between the drain and the gate came out because we were trying to correct for the difference in currents that was accruing if we were not biasing it. If we were not biasing it in such a way that the current drawn by the transistor and the current pushed by the current source match. So ultimately, the whole purpose is to ensure that this current and this currents match while keeping the transistor in saturation. If they don't match, which means we have to take some corrective action. And the corresponding corrective action in this case was, if the drain moves up, the gate has to move up. We'll have to ensure that the gate moves up. If the drain moves down, we'll have to ensure that the gate moves down. The simplest way to go about doing that was to simply connect. So now you see the way I have written this statement, which essentially it naturally, this should naturally lead to the fact that I can apply current at the source, then observe let's say drain voltage and correct the gate voltage. This is one possibility. Similarly, I can apply current at the drain, observe the source voltage and correct the source voltage. That is another possibility. And what is the last possibility? Apply current at source and observe which voltage? Source voltage, and correct the source voltage, right? So 4 possible combinations. So we have done the top one. Let me try to see if we can complete let me try to see if we can address this one. Then I'll also cover the other 2 in some ways. So by the definition of it, so the application of the current source has to be done at the source. So now if we apply the current source at the source, we are not touching the drain. So let's say the drain is at some constant voltage. Drain cannot be lower than, it cannot be ground, because by definition drain is at a higher voltage. So just put it at the maximum voltage that is possible in the circuit, which is the battery VDD. So now the argument starts, right? So the argument will be, we have to ensure that. So by the way, if I just simply connect it like this, will it work? No, it's not going to work, right? So, okay, fine. So we'll follow the same argument as we followed in the other case. So what was the argument? Let's assume that this transistor is pushing in some current, IDS. And like before, let's assume there is a small capacitor associated. It helps in visualizing the movement of voltage. So let's assume that let's assume IDS is greater than I naught. Okay, so let's assume this. If IDS is greater than I naught, what is going to happen to the source voltage? It's going to go up, right? So excess current is flowing into the capacitor and the voltage is going to go up. So if that is going to go up, what corrective action should we take? Decrease the gate voltage. But I mean, I can take as well, I can say, essentially I can say that I can decrease the gate to source voltage. Right? Ultimately, the current is dependent on the gate to source voltage, not the gate voltage only, right? Affecting the gate voltage is one of the possible scenarios, but note that I am now saying that I am going to do this only. I'm not going to touch the gate, because we want to take the corrective action at the source itself, not the gate. Okay. So yeah, there was some comment. Yeah, increase the source voltage. So if we say that we don't want to, let me take a step back. And if I say that I don't want to touch the gate voltage, I cannot keep it hanging, right? I have to connect it to some fixed voltage, whatever it might be, right? So let's connect it to some fixed voltage. Just like we connected drain to VDD, let's say I connect it to some fixed voltage VGQ. So now, so if we continue the argument now, as he rightly pointed out, if IDS is greater than I naught, it essentially means that the corrective action should be increase Vs. Correct? Do you agree with the argument? If I break it down further, this means that if IDS is greater than I naught, we need to decrease IDS, right? Which means we need to decrease VGS, which means we need to increase Vs, because gate we are not touching, right? But do you see that this happens automatically, right? If IDS is greater than I naught, I don't have to do anything. The voltage, so the source voltage is anyways increasing, right? Because the excess current is trying to pour into the capacitor, and moment some current tries to go into the capacitor voltage rises, right? So essentially, just by connecting the current source to the source, it seems like there is some inherent correction automatically happening. You don't have to do anything. Yes. Yeah. It's a parasitic capacitor. I mean, this is just to visualize why the how the voltage is increasing. Assume it to be a parasitic capacitor, infinitesimally small value as of now. Okay. So assume that this tends to 0. I mean, this is just to visualize the time dependence of the voltage. Yes. Yeah, we'll do that. We'll do that calculation separately. But as far as we haven't yet ensured anything till now, just that we have ensured the sense of correction is correct or not. We haven't ensured that is the correction enough or not. That we haven't done. That is a part of the analysis that we are going to do next. But as of now, the first thing is to at least understand if we are going in the right direction. Right. So if you are convinced that the sense of the feedback, the sense of the correction is correct, then we can do the analysis. We can do the analysis and see whether this is enough. If this is not enough, what else can we do? Okay. So let's do that. Her point was, how do we ensure that, okay, I mean, it seems like the sense of the direction of the correction is fine, but how do we know that it is enough or not? How do we know the transistor is in saturation or not? Right? So firstly, what will ensure that the transistor is in saturation? Which condition will ensure that the transistor is in saturation or not? Yeah, so only the difference between these two voltages, right? Drain and the gate. So both the drain and the gate voltages are in our control, right? So we can set the drain and the gate voltages as we please. So that ensures the transistor is in saturation. The other thing to ensure is to observe is if the transistor at all on, right? Is the VGS higher than threshold voltage? So do you think the VGS will be higher than threshold voltage or not in this case at steady state where the capacitor is not in picture? It will be, right? Because from the very argument that I naught current flows, as long as I naught is large enough, you cannot say I naught is 0. Right? So as long as I naught current flows, then there has to be a channel that must have formed. Otherwise, I naught wouldn't have flowed. Now, if you are not comfortable with the argument, the way to think about it is that let's assume that the transistor is off. There is no channel. So you're trying to pull out current I0 from the source, from this node. If you're trying to pull out the current of I0, that node voltage is going to decrease. Moment that node voltage decreases, you develop a VGS, and that node voltage will decrease as much as it is required for the transistor to provide a current of I0, which means the VGS will automatically adjust itself to provide the current of I0. Right? Does that make sense? Extremely simple circuit. Analysis is also super easy. But to understand why why connecting a current source to the source works automatically, you have to appreciate the fact that there is an inherent feedback that goes on in a transistor. Okay. So if you are convinced with that, then the next thing is to understand, is there a limit to these? Yes. Right. So let's assume, so whenever we are trying to figure out whether there is a feedback or not, or rather in this case, negative feedback or not, what we are trying to see is, what is the core principle of a negative feedback? I presume you are doing negative feedback in 250, right? So what is the core principle of negative feedback? Let's say you have a network, you disturb the network, the negative feedback will ensure that the network comes back to its original position, right? That's the whole purpose of feedback. It keeps the working tight. You disturb anything and it comes back. The network comes back to, or whatever system comes back to its original working operating condition, at least similar operating condition. So if we think about that in this way, in this particular case, so let's say you have connected like this, and let's say the threshold voltage changed. Okay, let's say the threshold voltage increased. Right. So let's assume the threshold voltage increased. So this is the disturbance. So now I have to see whether based on this disturbance, the network comes back to its original operating state or it diverges out. If it comes back, then we have negative feedback. If it doesn't, then we don't have negative feedback. Okay. So let's say the threshold voltage increased. Momentarily, what is going to happen to IDS? The moment threshold voltage increased at that particular moment, what's going to happen to IDS? It's going to increase or decrease? It's going to decrease, right? So if it decreases, what's going to happen to VS? So you are now pushing in less current than you are pulling out. IDS is less than I0. Then VS is going to decrease. Right? You are pulling out, I0 is not changing, but IDS is decreasing, which means you are pulling out more charge out of that node than you are pushing in, which means the source voltage is going to decrease. You see that? So moment the source voltage decreases, the VGS, what is happening to VGS? That is increasing. If VGS increases, IDS then goes back down. Right? So there is an inherent corrective action. So you try to change the IDS by changing threshold voltage, but circuit finds a way of figuring out how to keep the overdrive constant. Right? So there is a inherent negative feedback inbuilt into this network. So VGS auto adjusts itself to the value that is required to provide the current of I0. So in the earlier circuit, in this case, also VGS was auto adjusting itself, but it was doing it in a different way. Right? In this case, we had to establish a connection between the drain and the gate. Without establishing the connection, the feedback was not apparent. Because, again, whatever happens to the drain voltage doesn't affect the gate voltage automatically in a transistor. There is no dependence. In a basic, in a standalone transistor, there is no dependence of the gate voltage on the drain voltage. Right? But in case of, if you connect the current source to the source, there is a dependence because the current is dependent on VGS. So the moment you try to affect the source voltage, you are affecting VGS, and therein lies the negative feedback, right? So another way of visualizing this is through the small signal model. And the small thing, if you see the small signal model of a two-port network is this. So you have a bunch of stuff connected here, you have a bunch of stuff connected here. So this is the input port V1, this is the output port V2. But in a transistor, these two ports are connected. Right? So this is the source port. In a NMOS transistor, this is the source port. In a PMOS, you just flip it, put the source on the top. But you see that there is a connection between the output port and the input port, and that essentially is the feedback. It comes in as a package. You cannot separate it in a transistor. The feedback through the source terminal is always present. Okay. Okay. So, so the next thing to understand. So now, if you are convinced that this feedback is going to work, the next thing is to see whether transistor is in saturation or not. And that we discussed. It is totally in our control that you can decide the values of VDD and VGQ as long as VGQ is not more than 1 threshold voltage above VDD, you are good. Okay. Okay, fine. So the next thing that we need to then figure out is, again, this was something was there in the assignment. So let's say I don't want to connect a current source. Again, the issues with current sources are similar, that you cannot have floating current sources. Sometimes you have only one current source, just like you have one single battery, and you use the same current source to bias all transistors. So you cannot have one current source for each transistor in the network, right? So you can have like thousands of transistors. So that doesn't mean you can have thousands of current sources. There has to be one master current source, just like you have a master VDD, and derive the requisite current from that current source. So what we have to do is figure out a way of getting this current. Okay. Assume that we have one single current source and we have like this type of hundreds of circuits. So how do I ensure that from one single current source, which is floating somewhere, I derive all the requisite current? So let me rephrase the problem statement. The problem statement is, let's say I have a current source I0, and I want to ensure that somehow I do something so that this current is also I0. And let's assume I have many of these networks. I have like hundreds of these transistors to bias. Okay. So can you suggest a solution? You have seen this in the assignment. You have seen this circuit. Pardon? Can you repeat? I0 the one and takes the same potential across all these. How do I do that? No, you mean I connect it here? And if I connect it here, then firstly, that direction is not correct, right? So, but we can argue that, let's say the direction is this way. But if I connect it here, then there is a division of current, right? Great, right? So essentially, see, we have this circuit. We have this one. So I can borrow this circuit, right? So what I can do is, okay, so even before going here, so we know that if, let's say, if I have a transistor which is biased in saturation, right? If, let's say, I have, this is M1, this is biased in saturation somehow, right? So what is this current? This current will be IDS of M1, right? So this IDS, let's say I did the calculation and biased it such that this is of the value of I0, where I0 is a given current source. Some hand calculations I did, and I biased it at I0. And I also ensured that, somehow I ensured that M1 is in saturation, right? So if I ensure that M1 is in saturation, then naturally, I can ensure that. So, well, it's not naturally. So let me ask you this. So is there any way that I can do, that I can change the W by L or this biasing of the top transistor so that this I naught can change in this configuration, assuming the top transistor and the bottom transistors are in saturation? I naught depends on the lower transistor. As long as M1 and M2 are in saturation, then I naught only depends on the lower transistor, which is IDS of the lower transistor. It doesn't depend on M2. Right? Again, why does it not depend on M2? It does not depend on M2 because if I take an isolated transistor and let's say I have a constant VGS, right? So whatever I do to the drain voltage, this current is not going to change. Because in saturation, the current is not dependent on the drain to source voltage. Right? So essentially, a transistor in saturation is a current source or a current sink in this case, right? An NMOS transistor in saturation is a current sink because so what is one of the properties of a current source or a current sink? I keep changing the voltage across it, current is not going to change. So similarly, if I ensure that your transistor is biased in saturation and I keep changing VDS, while obviously putting in a limit that VDS cannot be lower than something, your current is not going to change, which means your transistor can behave like a current source or a current sink in this case. So in essence, this is a current source as long as M1 is in saturation. So now, but we know better now because biasing it like this is an issue. What is the issue if I bias it like this? With changes in threshold voltage, with changes in ambient, IDS is going to change. A good I naught is supposed to be constant regardless of change of ambient conditions, right? So this is going to change. But I gave you an I naught. Which essentially means that I have to find out a way of ensuring this I naught flows through this. Add current source in source of M1. Okay, so then we'll be back to square one, right? If I add here, then what do I do for this transistor? I have like dozens of them. Then I have to add I naught to the sources of all of them. Right? I have one single current source, not multiple. Yes. Okay, hold on. Yeah. Yeah, true. I mean, what she is pointing out is, I mean, let's say I have 10 of them. So I connect one here, one here, one here. I mean, one trans. And then put a current source there. But I mean, these type of circuits we are going to use for some purposes, right? So ultimately, biasing is just a means, but there is an overall purpose that we want to serve. So just because I'm not able to bias, I don't want to change that configuration. Okay, so I want this. Yes, we are using, I mean, we are using that property of the transistor which makes it behave like a current source. But the issue is the current is not constant with the change in temperature or threshold voltage. So you had another point? No? Okay, so again, I mean, so if we know that, let's say I'm not limiting you to one transistor or two transistors. So one good thing about integrated circuit is that value of a transistor is very small. I mean, you can use like hundreds of them if required. So it's not like a breadboard that putting one extra transistor means that you have to work for 1 extra hour. So you can keep on putting transistors as long as the purpose of the circuit is solved. Okay. So we have now till now only seen two configurations. So solution is there in those two configurations. So can you think of a way? So again, how to go about thinking about it? Putting a fixed VP1 is a problem. Putting a fixed VP1 is a problem because if the threshold voltage changes, this IDS is going to change. We don't want to put a fixed VG1. One way to say that, let's connect this, right? So let's connect this. Okay, so now let's think about this. If we connect this, so what will be the voltage at this node? So before calculating the voltage at this node, can you comment on what's going to happen if this voltage increases or decreases? If there, let's say the voltage increases, right? If this voltage increases, this transistor M1 is trying to, the condition of M1 is asking for more current to be sunk in. But what is the condition on M2? What is happening to M2? VGS is going to reduce, which means M2 is trying to reduce the current, right? So there is again an inherent feedback mechanism associated with this. Okay, so it's going to set to some value of current for which, I mean, in this case, the VGS of M2 and VGS of M1 are same, right? You will get some value of current, but that value of current is not set by you. It's not set by a current source. Another problem with this architecture is what is the impedance looking down? Incremental impedance looking into this configuration.
So, what do you think about how that voltage increases? What happens in?
So let's say this voltage increases. The condition on M1 tries to ensure that this current increases, right? Because VGS increases. But the condition on M2 tries to decrease the current because the gate is constant, source is increasing. So there is an inherent feedback which will set the current, but the value of the current need not necessarily be equal to I0 that you intended to be, right? So this circuit has its applications, but not with regards to whatever we were trying to achieve. Okay. So another reason it will not serve the purpose is the following: that what is the in an ideal current source, what is the impedance looking into the current source? You have an ideal current source, and I'm looking across the current source. What is the impedance of a current source? 0 or infinite or finite or something? It's infinite, right? How do I know? I change the voltage, no current changes. Incremental, if I change voltage, no current changes, which means it's an infinite impedance. So what is the impedance looking into this configuration, into the drain of M1 in the way that I have connected? Incrementally, you can do the calculation and tell me. Replace this M1 with its incremental equivalent and tell me what is the impedance. Pardon? 1 over GM. Right? Why 1 over GM? Because ultimately, so you have a gate. The gate gets connected to the drain. Source is grounded. And where am I looking at? I'm looking at the drain, right? This is the drain. So what I do, I apply a test voltage. The drain and the gate are the same, right? So this current will be GM times Vtest, because the gate voltage is Vtest and source voltage is 0, which means you are drawing in current of GM times Vtest from Vtest. So the impedance is 1 over GM. This is the same thing that we did in the previous class, right? Of a diode connected transistor, the looking in impedance is 1 over GM. So it's definitely not infinite. Let's say your GM is 1 kilo, GM is 1 millisiemens or 10 millisiemens. Your input or the resistance looking into this configuration can be 1 kilo ohm or 100 ohm, depending upon what the value of the GM is. So not only it's not infinite, it can change based on what is the value of GM quite drastically. So even though this circuit seems like this is going to solve the purpose, and while doing intuition-based design, doing an analysis looks like it's not going to serve the purpose. So one of the reasons it's not able to serve the purpose is because change of this voltage, change of the drain voltage is feeding into the gate and changing the current. Right? It's not acting like a current source. If I have to make sure that M1 acts like a current source, I have to leave the drain alone. I cannot have part of the information of the drain flowing in, affecting the gate or the source voltage. Okay, fine. So this is not going to work, but still I want this VGS. I want the VGS for the requisite amount of current, and this VGS should be such that it automatically adjusts itself with regards to the if there is a change in threshold voltage or mobility or so on and so forth. Right? So how do I, now the problem statement then breaks down to, or rather reduces to, how do I generate a VGS which is equipped to give me a constant current? Let's say you can use more transistors, but that is the problem statement. Give me a VGS which is equipped to give me a constant current. Can you think of a way? So how will you argue? I want a VGS which gives me that magic voltage for constant current. Somehow I have to generate. So what will be the argument? When current decreases, VGS should decrease. When current increases, VGS should increase. Do you know a circuit which does that? This is only for biasing, right? Capacitor will not help. Either it will be open or it will be, it will be open, right? For DC. You have a current source. Current source is given. You can use more transistors. So what about this circuit, right? What about this circuit? The top left circuit. So do you think the VGS of this will adjust itself? Right. So I can use that then, right? So I can use that. I can use a separate transistor here to generate this VGS. This is the VGS that is required to get the current of I0. Right? If threshold voltage changes, this VGS can adjust itself. It can go up or down depending upon the requisite I0. Right? So now, and the good thing again of integrated circuits is similar transistors which are placed very close by almost always have similar threshold voltages. If one changes, the other also changes. So for all practical purposes, you can assume that all these NMOSes are identical if they are sized identical. Yes.
Say that we need to power all the transistors.
Yes, we'll come to that. We'll come to that. Yes, one step at a time. So now let's say we have this. What is the solution? Yeah, right. So we can connect these two. Right. So let me redraw this. Was M1, which was M2. We call this M0. Okay. So are we satisfied with the fact that this is going to work? Okay. For now, let's say I have another case. Let's say M4. So I need a current source here, but I cannot use the current source there. So what am I going to do? So I will use another transistor. Transistors are almost free. I need to generate this VGS. So from where will I get that VGS? Do I need to use another set of this diode connected transistor, or I can reuse something? Yeah, I can reuse, right? So I can essentially say that this voltage is the same that is required. So I can keep drawing. And this I can do because connection of this infinite number of MOSFET gates doesn't load, right? So this IG is 0. Because IG is 0, connecting this does not divert any part of I0 into any of the gates. So that voltage doesn't change. Had Ig not been 0, then it would have been a potential problem. Okay, so you'll see later on, this is a potential problem in BJT-based circuits, where the base current in that case is sometimes is more often than not 0 or not negligible. So there are some circuit techniques which take care of that. But if Ig is 0, we are good. Don't have to bother. Okay. So now if you have if you want 10 of them, you can keep on connecting and you can bias all transistors, right? Okay, fine. So any questions on this? Does that mean? Okay, so you can, so depending on, okay, so let's say I have one path. Let's say I have one path. The current through this path is I0, right? And for this only that stack, what is the power consumption? The current multiplied by the voltage, the total voltage is VDD. So I0 times VDD is the power consumption through that one single stack. So if I have 10 of them, then obviously I'm consuming 10 times that, right? So in principle, yes, if you have infinite of them, you are going to have infinite power. So that's why you cannot go crazy with that. Okay. So if you are convinced that this is going to work, the next thing to see is, moment you connect all these things with real transistors, you have to be bothered about biasing points, right? Ideal current sources, ideal voltage sources, you don't have to worry about biasing. But in this case, you probably will have to worry about biasing. So how do we ensure? So firstly, when we say about biasing, we have to ensure that the transistor remains in saturation. The condition of M0 is pretty straightforward. Drain and gate are always connected. So it's in saturation. Don't have to bother. But what about M1? What do we need to ensure that what do we need? How do we need to size M1 or M2 in order to ensure that M1 remains in saturation? For that, we first need to figure out what this voltage is, which is VGSQ. Now this VGSQ is nothing but the threshold voltage of M0, which is same for all transistors because they are sitting on the chip, times 2I0 by UNC ox W by L. Okay, so this, by the way, is also the overdrive voltage, right? So let's say we have found this VGSQ. We have to ensure that M1 remains in saturation. So what is the thing that I need to observe to establish whether M1 is in saturation or not? Exactly. So we have to observe the drain voltage. Great. So VD1. So now the question is, how do I figure out what is the drain voltage of VD1? We know the current. Yes, we know the current. This is I0. If M1 is in saturation, this current is I0. So what will be? Overdrive of what transistor is important in this case? Of M2. Right. So the question that I'm asking is that who is setting the voltage at VD1? It is M2, because think about it, M1 is essentially a current source. If everything is working properly, M1 is a current source, and depending on the value of the current source, VD1 will go up and down because the VGS of M2 will auto adjust itself. Right? The gate of M2 is constant. If the VGS auto adjusts, which means the source is going to go up and down depending on the requisite current that M2 wants, right? So in essence, this current, so another terminology that is often used is when you see a multiple transistor stack, a designer will often ask you, or somebody who is maybe interviewing you will ask you, who is setting the current in this stack? I have like 5 different transistors, and I know that transistor equation is mu NC ox W by L VGS minus VT whole square. So does that mean if I increase W by L of all transistors or any transistor, the current is going to get affected? Or there is one dominant transistor whose W by L is directly influencing the current? Okay, so in this case, when I have the stack of M1 and M2, if I change the W by L of M1, will the current change? Yes, Pretty evident. If I change the W by L of M2, will the current change? No, right? So why not?
Current is dependent on
Current is dependent on the current source, but if let's say I am only observing M2, I'm only observing M2, and a blind observer, I'm only observing M2, I'm changing the W by L of M2, but I'm seeing that current is not changing. Then is the equation incorrect? Yeah, so VGS is changing, right? VGS is adjusting itself, right? So increasing the W by L, increasing the size, changing the size of M2 is not affecting the current. Hence, M2 is not setting the current in the stack. Okay, so the current is getting set by M1 and M2 is playing along. M2 is auto-adjusting its VGS, right? So which means that VD1 is, I can write VD1 in this case as, so essentially VD1 is equal to whatever this was, let's say VB2 minus VGS for a current of I0, and which is VB2 minus threshold voltage plus 2I0 by mu n C ox W over L. Okay, so now we have some handle. We have to ensure that if M1 tries to M1, we have to ensure M1 is in saturation. We have to ensure that this voltage is greater. This voltage is greater than VGSQ minus the threshold voltage. Okay. Okay.
M1 is equal to VB2 minus VGS. Yes, sir.
So we have to ensure that M1 remains in saturation, right? So condition of saturation for M1 is what? VD1 should be greater than VGSQ minus threshold voltage. So that's just that I'm rewriting that. So VD1 is set by M2, right? So VD1 is set by M2. So this becomes VD1. This should be greater than VGSQ minus the threshold voltage, right? Does that make sense? Yes or no? Okay, so let's say as a designer, you did all your calculations and you hooked the circuit up and you see that M1 is probably, maybe you did some calculation mistake or something went wrong, right? So M1 is not in saturation, M1 is in linear. So what is the thing that you will do to bring M1 out of saturation or out of linear into saturation? Decrease VGS, correct? Decrease VGS of M2, right? Of the top transistor. Correct? Decrease VGS of the top transistor. I don't want to change I0, right? So decrease VGS of M2, because basically I want to increase this. I have to increase VD1. If I have to increase VD1, I have to decrease the VGS of M2. Gate, probably I haven't changed. So what is the only handle? See, only you have voltages, gate, and W by L. There's nothing else. So what are you going to do to W by L of M2? You have to increase the W by L of M2, right? If you increase the W by L of M2, then VGS is going to decrease. Gate is constant, which means the source of M2 is going to go up, right? So this is one other part of being a designer. You have to understand which is the dominant knob, right? So ultimately, each transistor is a knob to change something. So what you want to change and what is the knob, right? So in this case, if you have to influence the drain voltage of M1, if you have to influence the drain voltage of M1, M1 doesn't have any role. You have to change M2 because M2 is the knob. Okay, so it's important to understand the knobs because equations are all the same. There is only one single equation. As long as you understand the knobs, everything is simple. Okay. Okay. So before we end, any questions? Okay, so in that case, we can stop. Thank you.